No, no. Hello and welcome back to Calculus 2. It was Mark opening the session tonight. And we're talking about the polar coordinates 10.2. There's your flower. What are polar coordinates? Well, let's understand first the differences, and hopefully it will be clear once you see how they behave. So r comma theta, that's how polar coordinates look like. So you have your good old rectangular coordinates, also known as Cartesian, and then you have polar coordinates as r comma theta. R is the radius and theta is the angle. So if I have 3, 5 in rectangular coordinate system, I will count 1, 2, 3, and then 1, 2, 3, 4, 5, and that would be the point on Cartesian xy plane. R theta might be, let's say, 3 pi over 4. You see that r is the radius, it's a length, and theta is the angle. I can write 45 degrees or I can write pi over 4. So now the way that would graph is we graph 3 on the x-axis, and then we swing that to pi over 4. Now pi over 4 is the 45-degree line, so this would go this way, and here's that point, 3 pi over 4.
But that line, that black line, that's the angle pi over 4.
Yeah, we don't need anything, it's a construction line. So I just showed that I swing this, right? That's all it is. I swing that for the pi over 4 angle. So that's pi over 4. So we first draw 3 from origin, because you can have -3, then you draw negative side. Positive angles go counterclockwise and negative angles go clockwise, because you can have all of the combinations.
Why are you not at the point where 3 is a line? Why are you over 2? And you're getting that 45 degree angle. I don't understand why you picked the point you picked on the right line.
I didn't pick any, it's just that this distance here, which I can call, let's call a distance d, needs to be the same as the distance d on this line. They have to be the same distance. And then diagonally, right, diagonal of the square is not the same as the side.
Right.
So it should probably go a little bit higher, but I didn't put it up. So what are the polar coordinates? Polar coordinates is a different way to get to a point on the coordinate system. This coordinate system is still xy coordinate system, except now the way we get to a particular location is you draw the radius and then you swing that for the angle that it's given to you. We actually get to the same point in a different way. And we'll see the conversion between the two. We will see the benefits and the drawback of polar coordinates. They are not all perfect, because polar coordinates would be all we use. In some cases, we will stick with the rectangular. In other cases, we will stick with polar. You must learn both, not just to survive Calc 3, but to actually work with certain systems later on in mathematics and engineering. So the first order of business for us is to learn how to quickly graph points and understand how the polar system works, because that will help us later with setting up integrals and doing calculus. These polar coordinates will be upgraded to three-dimensional coordinates later, called cylindrical coordinates, and then spherical coordinates. So there will be two different upgrades to polar coordinates in Calc2. Your rectangular coordinates x, y will only be upgraded in one way, comma z, and that's it. You get a box, like the box we're sitting in right now, called the classroom. But if you have r comma theta and you add z at the end, what you do is r comma theta gives you the circle and z gives you the vertical up. It's a cylinder. And if you have another angle involved, z comma theta comma phi, you will get cylindrical, spherical coordinates, which is the ball. So you really need to know this if you are going on with your coursework. So let's take a look at graphing -2 and pi over 6. -2 and pi over 6. So we draw xy coordinate system, as we usually do. Graph -2 on x-axis. And then, where do I go? Up or down? Pi over 6, 30 degrees. Down. Has to be counterclockwise. Positive angles. This is pi over 6 line. So, right there. Let's call this point A, so I don't have to write this 15,000 times. Let's take a look at point B as 3, comma, -pi over 3. Try this one on your own. So 3 -pi over 3.
How do you integrate that? Is it just the same thing? Same thing is because if it's 10x, you don't integrate 2 times it.
Do we all have 1, 2, 3 on a positive axis? And then we go clockwise, so down 60 degrees. So it's going to end up somewhere over there as a point B.
I mean, I got that right direction, but my angle was a little off.
That's okay, because starting next class you will be bringing protractor everywhere you go, and
I mean, it's the last class, so. Actually,
it's a sketch.
like,
It is,
this is really hard.
I mean, you should be, but then such is life. Point C, -4, -pi/4. Are we all good on this? -4. Where do I go, up or down? Up, clockwise. Oops.
Well, why do you go upward again? Because it's a negative negative?
No, negative angle means go clockwise.
Okay,
That's completely independent from -4,
gotcha.
which is to the left. One more. How about 4 3 pi over 4? Just to brush up a little bit on your.
Right after the 4 5 over 4 equal to. I kind of completely forgot my name. You're talking to a guy that completely forgot his unit circles. Yeah.
Half circles, pi. Whole circles all the way around. This is pi.
Oh, so
So
it's
you
like
just
here.
take pi over 4 would be this. Pi over 2. Basically, here to here, that's pi because that's half the circle. Whole circle is pi. So if you know this is half pi, you just put that. So 3 pi over 4 would be like 2 here.
Yeah.
So think of it more
You know what's
like,
funny? That's
think of it more like you're going a distance of 3 pi over 4 rather than looking at the angle that's
Gotcha.
that's what made the last 2 minutes. Like on C, for some reason I tried to go all the way around to this side. No, it's just like distance.
Okay, so you get to see if we get the lead on anything else.
Yeah, I'm gonna go stop. And Derek Rose is really not playing because he said his back hurt him today. Like it was sore. Derek Rose, basketball. Dude, you have a $25 million contract, and all you have to do is play 82 games. All you have to do. Maybe a little more, including the playoffs, but you get a bonus for each of those games.
All right. So now, what do you get?
That's assuming I get 80.
What is the answer for this one? Dot.
It's like, yeah.
Okay, so yeah, we got the same graph. Absolutely the same graph, same location.
What would you get positive 4?
Yeah, so
Exactly.
But the point is in the same.
But you do three.
Point is in the same spot.
Yeah, point is the same spot. But that's the answer. It's just a point. Whoever said point, someone said point. You said, right? The answer is point. You are graphing a little dot. It's a location in the two-dimensional universe over there. And as you can see, points C and D are the same point. And this is the new feature of polar coordinates. You are able to represent the same point in infinitely many ways. Because every time you go 2 pi around on the same radius, you land on the same spot. I mean, think about it. Don't do this, but think about it. If you go to a traffic circle, right? You can exit on your exit immediately, or you can drive 5 times around and then take the same exit, right? You are at the same exit. By the way, that's a ticket if you do it.
Really?
Yeah.
How
Yeah.
do you know?
Let's say I know for a fact. Don't worry about it.
You can do that on the circle. You weren't here for the old circle, were you?
You can do it for any circle. There are 2 in Flemington and so on. But don't.
You're right.
sucks.
Yeah, but 200 J's. Oh yeah, the third one's over. Yeah. Okay.
Yeah, but how would they know that?
Just don't worry about it. It's just take it as that they know. Okay. Everything is known. So the new feature of these coordinates, guys, the only way to represent 3, 4 in rectangular coordinates is the dot 3, 4. There is no other way to represent 3, 4. But here's the example where I show you the same location written that way or that way. Now, if I am to go plus 2 pi, right, that would add, so it will be 11 over here. It's going to be the same location every time. So 11, 19, 27, right? I add 8 every time because it's over 4, right? 2 pi, so 2 pi, 8. So keep adding 8. And every time you add or subtract 8 from this value, it's going to land in the same spot. Every time. It goes around, same spot. So polar coordinates have that extra feature that each point on the plane can be reached with infinitely many times, right? There are infinitely many ways to get there. Now, obviously, you have to be with the same radius. And you see also that if the radius changes from -4 to +4 and so on, we can play with that as well. So it's like 2 times infinity. Chuck Norris would understand that. He's the only one who can count to infinity.
Did you know
Twice.
He is so
In 5
tough
minutes.
that his beard is just another fist. You knew that?
Yes, pushes the earth. I know over 100 of those truths. Do not speak ill because... All right. The next part is to figure out the way to convert between the two systems, because we clearly graphed all of these polar graphs on xy plane. So there has to be a corresponding point in our xy rectangular world. And there is. So if I draw a random point here, I will have these features to it. There will be x, there will be y, there will be r, and then there will be a swing theta. What are the equations that you can write regarding this triangle? You can clearly write
X squared plus y squared equals r.
x squared. So you can clearly write Pythagorean theorem, right? So if I write x squared plus y squared is equal to r squared, from there I can say that r is equal to square root of x squared plus y squared. I know I should be plus and minus, but lengths are never negative. Radius is always positive value. So you can clearly see that that particular equation there gives you the connection. If you have both of the, if you have a Cartesian rectangular one, you can calculate the radius easily. Great. Now, how would you calculate theta? Well, that will be the inverse tangent, because tangent theta is y over x, then theta is equal to inverse tangent of y over x. So these are the two conversion formulas. I will write them in red. As you are converting rectangular into polar, you will use r equals square root of x squared plus y squared, and theta equals inverse tangent of y over x. Inverse tangent is featured on your calculator as tangent minus 1, or for some of you now on your cell phones through the app. The rest of you upgrade your phones.
You got me,
Professor. There's much more from that account. The next part is to write both sines and cosines functions here. So sine theta is equal to opposite over over hypotenuse, which is y over r. And from here I can write that y is r sine theta. I can also write cosine theta is x over r, from where x is equal to r cosine theta, which gives us the other two equations for the other conversion, polar into rectangular. X is going to be r cosine theta, and y is r sine theta. So it should make sense when you look at equations. Look, you have both x and y given to find r and theta one at a time. In the other set, you have r and theta given to find x and y one at a time. So it should be fairly quickly, right, in common sense, which way they go without even remembering which one is which. Also, they're extremely easy to derive. You must know these formulas, obviously, for the final, but you must know these formulas for Calc3. Otherwise, you're doomed. All right? So now, we can change points from one to other. Let's see what are the, I don't know, 3,7, right? 3,7, convert that. Convert that to polar. 3,7. You can use your inverse tangent. Just be mindful of the mode of your calculator, guys. If you want to get the answer for theta back in degrees, make sure your calculator is in degree mode. A lot of mistakes along the way happen because you can only graph in radians, and then you have to switch it.
You still keep it in polar, or do you change that?
Yeah, polar is fine. That impacts your graphing only. But you have to switch radians degrees. That's the third line or whatever it is.
So do they want data to be in degrees?
That is your preference. That is your preference. For engineering, we usually have it in degrees. For purposes of math class, we always use radians. But with 7 and 3, you can't get like pi over 4 or pi over 12.
Yeah.
So yeah, so change it to degrees when it's something like this. Like if the points over there were 2 root 2, then you would get pi over 4 back. So it's like, yeah. Woo. All right, but
The little details that change degrees in the radius squared and cosine. How
Yeah.
much or you will try to send something else. You would actually go to
Yeah.
It's like vectors.
the difference between
So let's speed up. I need to speed up before I die.
6.28 radians. So your rocket would be
I'm never giving that one out. I read it on the paper. It was actually a course, so she's not taking it, but it was.
It's just like this.
I actually get this a lot more than I want that's the right hand.
Negative K, positive J, negative I.
66.8.
No, positive, negative K, positive J, negative I, positive I. Positive. Andrew's more precise. Positive K.
It was done on a Samsung phone, okay?
No, negative K, and it didn't use the J.
All right, let's take a look at this conversion together.
No.
I switched 3 to 5.
R is given by the square root of 3 squared plus 7 squared, which is 9 plus 49, which is the square root of 58, which is approximately 7.6. Thank you very much. Yeah, if you don't have the calculator, guys, linear approximation from Calculus 1 would work. Same goes for tangent inverse. So we have theta is equal to tangent inverse of y over x, which means 7 over 3, which is 66.8
I have this on degrees and it's not allowing me to do it. There's something
degrees.
wrong with my calculator, I think.
Is it Apple calculator?
No, see, this is tough, seriously, this is tough, this is on degrees, right? Is that a 0.6, that's on degrees, right? Yeah. Okay, so. Inverse tangent, oh, that's what I did wrong. Although let's make sure it's right, because it's still coming out with a degree. Now,
All right, let's convert one more and then do something else and be done with this section. So convert negative 2 pi over 6 to Cartesian, rectangular.
Instead of using theta, you just use pi over 6. That's negative 3 times 3 times, that's it.
R sin theta. R is
Yeah, but you have to make sure you know the right move.
yeah, I have that. Negative 3. Oh, yeah. Yeah. Oh, yeah, yeah, yeah. Yeah, the coordinate variable is negative 3.
-1 for y. And -1.7 for
I'm gonna get I come
Hey, Professor, if you was walking around the streets and just saw a guy dressed up like Spider-Man and a guy dressed up like Batman fighting,
I'm sorry?
it was like this video of like Spider-Man, Batman, and Robin fighting. It was like a street fight.
Uh-huh.
And Spider-Man like killed both of them. Like
Not literally.
not like literally, but like Spider-Man literally beat up Batman and Robin together.
Literally. Yeah, but not video.
Like, who do you think won the fight between Iron Man and Batman? Iron Man and Batman.
Like this.
Me?
Batman, you think? Iron Man?
Just needs to stand like this. What's Batman gonna do?
But I mean, Batman can build his own suit.
Why did you do
Yeah,
it
you
already?
can put an EMP.
Batman trumps all.
I mean, Batman did beat up Superman.
Yeah. It's a fiction. You can write whatever you want. Be realistic. This goes live on a stream. I'm gonna. Superman can fly. He picks him up. He just drops him off of Mars or something.
Like,
What do you have kryptonite?
You have 20 minutes left.
Yeah. Oh no, I have to finish this. So, but they ask questions. I mean, I
They
can't.
asked, what is with boys in this? Will Superman be?
alright, Superman versus Goku.
Good question. It's almost like an IQ test. It's almost like an IQ test. All right. So here's our step number 1 in understanding how polar coordinates are complementing the world of rectangular coordinates. They are not in competition. They are complementing each other. Observe the fact that what's beautiful in one world is bad looking in the other, all right? Here's the point in rectangular coordinates, and there is the polar equivalent, and here is the polar coordinates, and here is the square root of 3, right? I could have made it much worse if I just came up with something over here, right? That would have been much worse there. If this was 5, then the 2's don't cancel, and you get root 3 over. Just terrible. So this is the first step. Now when we understand how to deal with points and conversions, we are going to move on to polar functions, because we can have polar functions. Now you did see how the polar function for sine looks like. It's a flower, right? So sine of 2 theta gives you a 4-petal flower. A 4 theta gives you the 8-petal flower. Sine of even, or cosine of even number of petals will double the number of, right, whatever you have, and if it's odd, it's that number. So 3 is 3 petals, 5 is 5 petals, but 4 is 8 petals, 16 is 32 petals, and so on. now what I'm going to do is talk about the two basic functions. So, you know that when you are dealing with rectangular coordinates in xy, you have a horizontal and vertical line. So this is a vertical line with x equals to some value c, and you have a horizontal line which is y equals to d. These are the two cheapest, easiest equations that you can write. One is function, the other one is not. It's vertical line, right? But as you can see, these are the easiest equations because you get to describe the entire line with x equals c without mentioning y, because y takes on all of the values. It is important, as x component is important, or where the line is. And the y component in that case is not important because you're going to take all of the values from negative infinity to positive infinity. We have these equivalents in our polar world. So we're going to have an equation that says r equals a number. So r equals to 3. Now, what would be radius 3 that takes on all of the values of theta? What would that be? Circle. You see how cheap the equation of the circle is in polar coordinates? There's none of that x squared plus y squared, blah, blah, blah. It is just r equals to 3. So equation for the circle ends up being the simplest equation you can write for polar coordinates. Now that is really powerful. And then we have another one, theta. Let's say theta equals pi over 3. What would that be? Every possible radius, positive and negative, at pi over 3. What would that be? Straight line through the origin through pi over 3. Yes, very good. It is the straight line, linear line. Has to go through the origin, and you can find every single radius, right? Radius is 1, radius is 1.1, radius is negative 0.7, right? Whatever. When you put them all together, they dot the entire line. So these are the two easiest equations. That's how we compare it to Cartesian. Cartesian has a vertical and horizontal lines where you set each one of the x and y to a number. Polar coordinates will have a slanted line through the origin. Well, it could be anything, right? You see that you can get the vertical and horizontal in a single equation, right? It seems like it's far more powerful, but it does have limitations. And we'll see what those limitations are. Try to express the equation of the line that doesn't go through the origin. Yeah, you'll see the meaning of hell right there. So the next order of business is to understand polar functions. So you have the two easiest functions, right? Basic cases at the right. But in general, we say r equals f of theta for polar functions. And we use the same conversions to go between the two worlds. So how do I convert the function r equals 3 into rectangular? Well, I know that r is the square root of x squared plus y squared. I plug that in, equals to 3, and I just square both sides. Right? It's very cheap, actually. So we get x squared plus y squared is equal to 9, which we know it's the circle with radius 3. If you try to do this to any other line, anything else, it will work, except you'll see that it starts being really annoying when you start converting things that you really shouldn't be converting. Because, again, for the 5th time, these two worlds complement each other. They do not compete against each other. So what we are going to do now is take a look at, let's say, theta equals pi over 3 converted to rectangular. Well, theta is what? Inverse tangent of y over x is equal to pi over 3. I hit both sides with tangent to kill off the inverse. I get y over x is equal to tangent of pi over 3. Very good. And then I will multiply both sides by x, and we get y equals root 3x. Observe that plus b part is 0 because it goes through origin, right?
Yeah.
So theta equals pi over 3 is the same equation as y equals root 3x. Slope is root 3. You can convert anything, except it gets really bad in some cases. So how about our flower equation? Y equals, I'm just going to skip that part of 4 times sine. I'm just going to write it as sine, and let's use 2 theta because I would like to fit this on one page. Sine of 2 theta is going to give us 4 petals. Okay? And if I remember correctly, those 4 petals will be, hold on, what happened here? My calculator decided to leave the realm of polars.
Your wonderful Samsung.
Oh, no, 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 all good, all good.
It's okay, droids have minds of their own, they do their own thing. That's why they don't work.
They are self-aware.
Get caught up in their individuality. You think they're special. I see classes in the third floor of my That's okay, I was looking forward to more.
Oh, look at me writing Y. How silly. R.
Well, no wonder I was confused.
Yeah. So R equals sine 2 theta is the 4-petal flower. Cosine 2 theta would have these petals on axes, and sine has them there. Okay, so now So now, let's convert this into Cartesian coordinates, or rectangular, right? And see what happens. So remember, you are not allowed to have any of the thetas or r's around. So the first step would be to write this as 2 sine theta cosine theta, because you want to have single thetas functions, and then plug in conversions for r's and thetas. So r is the square root of x squared plus y squared. On the other end, you have 2 times sine of inverse tangent of y over x times the cosine of inverse tangent of y over x.
Before we go any further, I'm confused. How do we go from starting 2 theta to 2 sine theta cosine?
Formula from for a double angle, pre-calc.
Double angle.
I hope you remember it from the trig part of the integration.
That's right.
Yep.
But 2 times.
Now, you might remember these from your pre-calculus where you said, oh, why? Well, this is why, okay? The way to solve these is to draw a triangle on the side, label it as y, x, and r, and here be your theta. Oh, sorry, this one is square root of x squared plus y squared. Wow, Pythagorean theorem. I mean, which is r, but you write everything in terms of x's and y's. So now we have a square root of x squared plus y squared is equal to 2 times sine, and now you write the inverse sine. Looking at the triangle, sine is opposite over hypotenuse, so y over the square root of x squared plus y squared times the cosine, and now you write the cosine inverse, which is x over square root of x squared plus y squared. At this point, the functions drop, and what you get is the square root of x squared plus y squared is equal to 2xy divided by, when you multiply the square roots together, you just get x squared plus y squared. And now you bring x squared y squared to the other side, getting x squared plus y squared to the 3/2 is equal to 2xy, and you see that this is implicit, right? There's no way, comma, in hell, comma, to solve this y equals everything else. Can't do it. So this equation, if you type this in your Desmos, what is it called? Desmos, all right. In Cartesian, you will get the same flower for that you get for polar. But I don't think we have to do that optician trick. Which one is better? Right? Because I think we clearly get it that this one is better. That one is definitely better. Because you can do stuff with it, right? This thing, if you remember implicit differentiation, you can differentiate. But if you don't remember that, you can't do even that. So again, what's beautiful in one world, it's going to be ugly in the other one. These two worlds complement each other. We have time to try the conversion the other way, and then we'll do calculus next time. We still have a review on Tuesday, so we're good. Let's see. Let's take a look at a beautiful equation like y equals to 2x squared minus x plus 6. Something that you can maybe factor, you can find zeros, you can graph, right? Nice. How does this look in polar? It probably looks like living hell, right?
Yeah.
And yes, it does. What is y? It's going to be r sine theta. What is x?
R cosine theta.
Cosine theta minus r cosine theta plus 6. Try to fish out r somehow. Is it possible? The answer is kind of, because you can move all r terms on the left, but then you have r squared here. You will be able to factor one r, but there will be still one r floating about. So you won't be able even to solve it for r equals everything else. You cannot get something that looks like a function from this. Why? Because it looked beautiful in this world. That's why. It's very simple. So the best we can do is move these terms to this side. Equals to 6. Factor out single r, which will give me sine theta plus cosine theta minus 2r cosine squared theta equals to 6. And you see that there is that r that you can't fish out now. Because you would have to divide both sides by this parenthesis, and you will get 6 over this, but it will have r. So I can't write this as r as a function of theta. So keep the polar world in its own right, Cartesian world in its own, and in certain calculations it will be highly beneficial for you to switch. You will see calculus done in this next class, but then also there is this notion of calculus 3 coming up where you are going to build up on these concepts. So when you get a crazy looking integral that it's impossible to solve in Cartesian coordinates, it might convert into something that is a joke to do in either spherical or cylindrical coordinates. And for that, obviously, you'll be taking Calc2, chapter 13, and we will be dealing with that there. So I'll see you next semester in that course.
And I'll be laughing at you all for my statistics.
Me too.
Let me end stream and then make some comments. Bye, stream. Oops.